Hello, and welcome to Causal Foundations. I'm Naftali Weinberger, and I'm a philosopher of science who's been researching causal models for over a decade. In this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. Today I'm excited to introduce the one causal principle you can't do without. The principle I'll be discussing is called the causal Markov condition, and this is actually not the first time I'm discussing it. In episode 1, I introduced the principle of the common cause, which says that if two variables x and y are probabilistically dependent, then either x causes y causes x, or there's some common cause z that explains the correlation. In episode 2, we further saw that x and y can become probabilistically dependent, conditional on a common effect. I also defined d-separation, which captures the ways that two variables can be made independent along a path, which is a set of connected arrows. Z d-separates, or blocks, x from y, if z is a common cause, or on a chain, and one does condition on it, or a common effect and one does not. X and y are d-separated by z full stop if they are d-separated by z along all paths. Given these concepts, one formulation of the causal Markov condition states that if x and y are d-separated by z in the causal graph, then they're probabilistically independent conditional on z. This means that one can take any causal graph and determine which variables must be conditionally independent if it's true. As such, the causal Markov condition, or CMC, is the basic bridge principle for specifying the empirical implications entailed by a causal hypothesis. Note that while the principle of the common cause stated that if variables are correlated, then they're causally linked, the causal Markov condition states that if variables are not causally linked, in a way made precise by d-separation, then they are not causally related. Despite the distinct formulations, the basic idea is the same, and the causal Markov condition is in fact a generalization of the principle of the common cause. Today I'll focus on a different formulation of CMC. This formulation is logically equivalent to the one just discussed, but will be more helpful for giving you an intuitive sense of what it means. The causal graphs we're using are called directed acyclic graphs, or DAGs. Within a DAG, we refer to the direct causes of a variable as its parents, and its effects as its descendants. A standard formulation of the causal Markov condition states that every variable in a DAG is probabilistically independent of its non-descendants, conditional on its parents. So conditional on z1 and z2, x will be independent of these variables. Here it helps to know that Markovian means that what happens at each step only depends on what happened in the prior step. In the causal context, this means that outside of a variable's effects, any information it contains about any other variable is fully captured by the values of its parents. The causal Markov condition is only plausible given certain restrictions on the variable set. For instance, if we're considering only the variables x, y, and z, but w is an unobserved common cause of x and z, then x and z will remain uncorrelated conditional on y, even though y is their only measured parent. For this reason, it's common to assume something called causal sufficiency, which states that one's variable set includes all common causes of any variables in the set. Only given such a condition is the causal Markov condition guaranteed to obtain. Since we almost never know all common causes, how is CMC ever useful? The answer is we can give a semi-Markovian model, which uses double-headed arrows to indicate the presence of omitted common causes. Although the observed variable sets don't satisfy CMC, these models entail that the set would be Markovian if one included the omitted variables. A further restriction on CMC is that the variables have to be distinct from one another. For instance, if x is equivalent to a and b, and y is equivalent to b, then x implies y, and a correlation between x and y wouldn't indicate a causal connection. The same goes for any other way that x and y might be intertwined, such as if x is a part of y. A more interesting consideration is the grain at which the variables are represented.
Consider a cue ball that hits balls 1 and 5, such that one will go into the corner pocket just in case the other does. If X is the collision, and Y and Z are the balls sinking, then X is a common cause of Y and Z. But even conditional on the collision, one ball's going in is correlated with the others going in as well, contrary to CMC. Note, however, that if you precisely describe the positions and forces in the collision, this would entail that both go into their pockets. Omitting this information amounts to a violation of causal sufficiency. CMC implies that correlations can always be similarly explained if we give enough detail. This appears to be true for all macroscopic systems, though in future episodes we'll consider possible counterexamples from quantum mechanics. One could be familiar with causal methods and still not have heard the words causal Markov condition. CMC features explicitly in algorithms for selecting among causal graphs, but it is indispensable even in domains where it's not explicitly formulated. Consider the concept of identification that was covered in episodes 3 to 6. When one applies the backdoor criterion, one blocks the transmission of probabilistic dependence along non-causal paths, such that any remaining dependence corresponds to the causal relationship. But this only works if one presupposes that any genuine probabilistic dependence must have a causal explanation. If not, then even once one blocks the backdoor path, there still could be a correlation that was not due to the causal effect. So identification does not work unless we assume CMC. While identification is about measuring an effect given knowledge of a DAG, causal discovery algorithms seek to find the correct DAG, given a probability distribution. Today I'll be talking specifically about constraint-based algorithms, which choose among causal DAGs based on conditional independence relationships. These algorithms cannot in general pick out the unique graph, but typically only an equivalence class. Recall that the following graphs all entail that x and y are deseparated by z and nothing else, so they can't be differentiated using conditional independencies alone. Because of this, we say they're in the same Markov equivalence class. To further distinguish among them, one would have to either bring in additional variables, intervene, or use non-probabilistic information such as time ordering. The causal Markov condition isn't sufficient for finding the correct Markov equivalence class. Note that if you take any set of variables and draw an arrow between each pair, no variables will be deseparated from any others, so the causal Markov condition won't imply anything. To have a reason to omit any arrows, you need principles other than CMC. One of the best known principles is called the causal faithfulness condition, whereas CMC says that variables that are independent in the graph are probabilistically independent. The causal faithfulness condition says that if variables are probabilistically independent, then they're deseparated. Put colloquially, it says that lack of correlation implies lack of causation. Assuming both CMC and faithfulness would allow one to determine the Markov equivalence class of the true graph. Faithfulness is not generally true. Suppose that I cycle to lose weight, but the exercise leads me to eat more Pfefferkäsebreze. If these calories cancel out those that I burnt, there will be no correlation between cycling and my weight, even though exercise causally influences weight loss. So we have a counterexample to faithfulness. It still might be reasonable to assume faithfulness in some contexts, but there's nothing in the nature of causation that implies that faithfulness can't fail. The contrast between faithfulness and causal Markov helps illustrate why I claim CMC is indispensable. While abandoning faithfulness would make it harder to find the correct causal model, abandoning CMC would leave us without any idea of what we're even looking for. CMC is thus a foundational bridge principle, since it is necessary in order for DAGs to have any empirical consequences at all. Thank you for listening. For further information, check out Chapter 3 of Causation, Prediction, and Search, which remains the Bible for algorithmic approaches to causation, and in particular to those that use constraint-based algorithms.